Okay, so let me ask you something. Have you ever heard about a Nobel Prize-winning physicist who solved a national tragedy with nothing more than a glass of ice water? Or a guy who looked at the universe and thought, what if particles take every single path at once? Well, today, we're diving into the brilliant, totally unconventional mind of Richard Feynman, a scientist who basically decided to rewrite the rules of reality.
This quote right here, it's basically the key to understanding the guy. It wasn't just some nice-sounding phrase. It was everything to him. His whole deal was that nature doesn't care what we think. It doesn't care about our reputations or how beautiful our equations are. All that matters is what's real. And he was absolutely relentless about finding that reality.
And that's the thing. To really get a grip on Feynman's physics, you've got to understand the man himself first. See, his genius wasn't just locked away in his brain, it was in his entire approach to life. It was this mix of being playful, incredibly intense, and just having this relentless demand for answers. And nothing, I mean nothing, captures this better than what he did during the Challenger disaster investigation. So, it's 1986, right? The shuttle has just tragically exploded, and Feynman's on the panel to figure out why. But he wasn't sitting around reading reports. No way. He went straight to the engineers on the ground. He got a hunch it was about these rubber O-rings. So what does he do? In a live, televised hearing in front of everyone, he does something so simple it's brilliant. He just dunks one of those O-rings into a glass of ice water to mimic the cold on launch day and pulls it out. And right there, for the whole world to see, it's stiff, it's lost its springiness, it failed. In that one simple moment, he sliced right through all the bureaucracy and the noise and just showed everyone the simple, devastating truth.
Okay, so now take that same mindset, that demand for simple, physical truth, and imagine him bringing it into the world of theoretical physics. Because back in the mid-20th century, physics had a huge problem. They had this theory that was almost perfect, but that almost was a big, big deal.
Right, this theory was called quantum electrodynamics, or QED for short. And you can just think of it as the ultimate rulebook for how light and matter, things like electrons, talk to each other. And here's the crazy part. It was the most precise, most successful theory in the entire history of science. I mean, it worked beautifully. Except, it was hiding this massive, universe-breaking flaw.
This is where it all just went completely off the rails. When physicists tried to use their perfect theory to calculate something really basic, like what happens when an electron and a photon interact, the math just broke. I'm not talking about a small error. It didn't give a slightly wrong answer. It spit out the answer infinity for everything. It's like asking your calculator what 2 plus 2 is, and it just starts screaming at you. The whole theory was fundamentally broken.
So can you imagine? Physicists were in a total crisis. Their best, most precise theory of reality was giving them impossible, infinite answers to the simplest questions. It was like having this incredibly detailed, perfect map of the world, but every single road on it just leads straight off a cliff. The entire field of physics had hit a brick wall, a dead end.
And this is where Richard Feynman steps onto the stage. See, he didn't try to just patch up the old theory, to put a Band-Aid on it. Nope. He decided to just rebuild physics from the ground up. And he started with the question so radical, so out there, that it changed absolutely everything.
Okay, so for centuries, physics had been guided by this really beautiful, simple idea. It's called the principle of least time. And it basically just says that nature is efficient. Light, for example, to get from point A to point B, will always take the single fastest route. It's clean, it's logical, it just makes sense, right?
But then Feynman comes along, and being Feynman, he looks at this perfectly elegant rule and asks a completely bonkers question. He says, wait a minute, what if light doesn't just take the one best path? What if, at the quantum level, it takes every single possible path all at the same time? I mean, think about that. The direct path, the long winding path, the one that zips off to the moon and back first, all of them. This idea, which he called summing over all paths, was a complete and total break from centuries of physics.
But here's the thing about Feynman. For him, this wasn't just some cool, abstract thought experiment. It had to be real. Like he always said, a theory is completely worthless if you can't compare it to actual experimental data. So his wild sum over paths idea had to do more than just sound cool. It had to actually work. It had to solve that impossible infinity problem.
So, how in the world did this crazy, abstract idea of infinite paths actually solve a real-world problem? Well, it led Feynman to create a whole new language for physics. A language so simple, you could literally do it on a cocktail napkin. You have to understand, before Feynman, calculating these particle interactions was an absolute nightmare. I mean, we're talking about months and months of incredibly dense, frustrating algebra that maybe a handful of people on the entire planet could even follow. Feynman's method? It just threw all of that in the trash. He turned all that impossible math into simple little pictures, sketches you could draw on a piece of paper.
And these are the legendary Feynman diagrams. They're kind of like a comic book for particle physics, a cheat sheet for the universe. It's so simple. A straight line? That's a particle, like an electron, just cruising through space and time. That squiggly line? That's a force particle, like a photon, being exchanged between them. And the point where they all meet, the vertex, that's the interaction, that's the action. And just like that, with these simple pictures, those terrifying infinities could finally be tamed and calculated. He created a visual language for reality itself, one that even had these wonderfully weird ideas baked in, like a positron just being an electron that's traveling backward in time.
And the proof that it all worked? That came in 1947. There was this moment when another famous physicist, Hans Bethe, actually made a crucial breakthrough calculation while he was on a train ride. And it was Feynman's new diagrams that allowed him, and pretty soon everyone else, to finally make sense of it all. The crisis was over.
So you see, in the end, Feynman's revolutionary diagrams and his whole sum over paths idea, they weren't just tools. They were a direct reflection of his personality. They were playful, they were intuitive, and they were deeply, deeply pragmatic. It was just his way of looking at the world, turned into physics.
And you can just see this unique thread running through his entire life. I mean, look at this. It starts with his PhD thesis back in 42, where he first cooked up this whole path integral idea. Then in 49, he publishes the diagrams that change everything. Of course, that leads to the Nobel Prize in 65. And then decades later, in 1986, it's the exact same thinking that leads him to that glass of ice water at the Challenger hearing. The method was always the same. Cut through all the complexity and find the simple, essential truth, no matter how weird the path to get there might be.
Because ultimately, Feynman was so much more than just a scientist, right? He was a showman, an absolutely brilliant teacher. He was kind of a rebel who couldn't stand unearned authority, but he was completely in love with reality. He had this famous playful intensity. He insisted on rederiving all of physics from scratch, in his own language, not for the awards or the fame, but for the sheer joy of it, for what he famously called the pleasure of finding things out.
And you know, his legacy really makes you wonder. He solved one of the deepest problems in the history of physics, all because he was willing to play, to ask what if, and to not be afraid of sounding a little bit crazy. So it kind of leaves us with a question, doesn't it? What big problems could we solve today if we weren't afraid to be a little more playful?